So we have an option in the ninth question. For practice, we will solve all the parts. So the question is define the terms. The first part is mole fraction. So what is mole fraction? Mole fraction So when we have a mixture, the mole fraction is calculated as the ratio of moles of one component and the total number of moles in the mixture. So for example, if a mixture is of A and B substances, so for mole fraction of A will be so XA is the number of moles of component A, XB is the number of moles of component B. So the total number of moles in the mixture is XA plus XB, and mole fraction of A would be XA over XA plus XB. Similarly, mole fraction of component B would be so mole fraction is the ratio of number of moles of the component and the total number of moles in the mixture. So the second part is we have to define isotonic solutions. So what are isotonic solutions? Any two solutions which have the same osmotic pressure at the same temperature. So if we have two solutions A and B and we are checking at the constant temperature, suppose the temperature is the room temperature or any other temperature, suppose it is 273 Kelvin. So when we calculate the osmotic pressure of the two solutions, if they come out to be equal at the same temperature, the two solutions are known as isotonic solutions. So the next part is we have to define Van Hoff factor. So Van Hoff factor is actually the ratio of normal molar mass over abnormal molar mass. And Van Hoff factor is denoted by the letter small I. So Van Hoff factor comes into play when there is a combination in the solution when two type of atoms combine or separate out to give the nature as a separate particle. So it creates a difference in the molar mass when we calculate it using that equation delta IV equals to kbm. So the molar mass comes out to be different. It is because either the particles separate out or combine. So we calculate Van Hoff factor by the ratio normal molar mass divided by abnormal molar mass. So the next part is ideal solution. So what is an ideal solution? Theoretically, we say the solution so any solution that obeys Raoult's law under all the conditions is an ideal solution. We have some characteristics of an ideal solution. For example, delta H of mixing is always 0 for an ideal solution. Also, delta V mixing is 0. It is like when we delta V mixing is actually when we combine two solutions. So the change in volume from initial sum of the two solutions to the final sum of the mixture, it comes out to be 0, and same is with delta H. So the next question is, what do you understand by the order of a reaction, and identify the reaction order from each of the following units of reaction rate constant. So first, what do you understand by order of a reaction? So order of reaction is actually the sum of powers of each component's concentration in the rate law expression. So suppose rate law expression is R equals to K A raised to power X B raised to power Y. So the rate is a factor of concentration of A raised to power X and the concentration of B raised to power Y. So order of reaction would be X plus Y, the sum of the powers. So coming to the second part of the question, we have to identify the reaction order from the units of reaction rate constant. So since it is easy, the first part is so it should be a zero order reaction. Because the unit of rate constant K is the inverse of, it is the same as concentration, mole over liter, and rate also has the same units, mole over liter per second. So the order of reaction, the units of these two should be 0. So the order of reaction X plus Y equals to 0. The second part is so similarly, this shows that the order of reaction is 2. So it is a second order. And we can explain it similarly. So the next question is, name the two groups into which phenomenon of catalysis can be divided and give examples of both the groups with chemical reactions. So the two groups are so it is quite evident that the two groups are homogeneous catalysis and heterogeneous catalysis, and it is obvious from the name that homogeneous catalysis is where all the components of the reaction, all the reactants are in the same state, and heterogeneous they are in the same state. So we will see the example. So example is SO2 plus O2 gives SO3. Here all the reactants and products are in the same state, that is gaseous state. So example of a heterogeneous catalysis is here. This is an heterogeneous catalysis example. Here all the reactants and products are in gaseous state, but the catalyst is in the solid state, which is nickel and platinum. So here ethene is reacting with hydrogen to form ethane, and the catalysts are nickel and platinum in solid state. So the next question is, what is meant by coagulation of a colloidal solution, colloidal sol, and describe briefly any three methods by which coagulation of lyophobic sols can be carried out. So coagulation is basically the precipitation of the particles of a colloid. So the process of settling down of colloidal particles is called coagulation, or it is also known as precipitation of the sol. So next we have to give any three methods by which coagulation of lyophobic sols can be carried out. First one is the first method is by electrophoresis. So what is electrophoresis? In electrophoresis, the colloidal particles move towards oppositely charged electrodes. So we put two electrodes in the soles, and when we make a potential difference across the two electrodes, the colloidal particles separate out and they go towards the oppositely charged electrode. The second method by which coagulation of lyophobic sols can be carried out is by mixing two oppositely charged sols. And the third method, it is by addition of electrolytes. So in the third method, when an excess of an electrolyte is added to the colloidal particles, the colloidal particles precipitate out. So it is the next method of coagulation of lyophobic sols.